Start with a wall of spheres. Pack them as tightly as you like. In this flat picture, the tightest possible honeycomb. Now ask the same question in a space with 1,000 dimensions. That is not science fiction. Every phone call you make travels through a space like that. In 1978, two mathematicians found the tightest known ceiling on how dense any such packing can ever be. Then the problem froze. For 48 years, through the whole age of the internet that runs on these very ideas, nobody could move that number. Not by a hair. In 2026, it moved. And the proof did something stranger than breaking a record. It took humanity's most powerful tool for this problem, the tool behind the only perfect answers we have ever found, and measured its exact strength. There is a wall, and the wall stands at 1 over pi. This film builds that wall from the ground up. What packing means, why a signal is a sphere, how one simple test can judge every packing at once, and how a 48-year-old number finally moved. Every idea will be built before it is used. You need school algebra and nothing else. First, what exactly is being measured? Take equal balls that may touch but never overlap and fill space with them. Density is the fraction of space they cover. On a line, one dimension, segments can cover everything. Density, 100%. In the plane, the honeycomb arrangement is unbeatable at about 90.7%, and that is proved. In 3 dimensions, the grocer's pyramid fills about 74%. Kepler guessed it was best in 1611. The proof took until 1998, and a computer. Notice the pattern. Each new dimension leaves more unavoidable error, and each proof is savagely harder than the last. The window does the honest work here. Pack, frame, measure the filled fraction, and let the window grow. That limiting fraction is called delta D, the packing density of dimension D, one number for each dimension. Beyond dimension 3, almost every one of these numbers is unknown. That ignorance is the story. Why should anyone care about dimension 1000? Because you use it every day. Here's 1 second of sound, a waveform. Sample it. Measure its height 1,000 times. Now the whole clip is just a list of 1,000 numbers. And a list of 1,000 numbers is one point in a space with 1,000 dimensions. That is all a high dimension is. A long list of coordinates. Now send that point through a real channel, radio, fiber, a phone line. Noise jiggles every coordinate a little, so the received point lands somewhere inside a small, fuzzy ball around the one you sent. If 2 of your possible messages sit too close together, their fuzzballs overlap, and the receiver cannot tell them apart. To communicate reliably, you must choose messages whose noise balls never overlap. Look at what that is. Equal balls. No overlaps. Pack as many as possible. Reliable communication through noise is sphere packing in high dimension. Claude Shannon saw this in 1948, and every error-correcting code in your phone is built on this picture. How densely those balls can pack decides how much information a noisy world can carry. So we need dimension 1000. Can we just draw it? No. And here's the warning that makes this subject strange. Watch the volume of a ball, 1 unit across, as the dimension climbs. Dimension 2, 3, 4, 5. The volume rises, then it turns, and it collapses. By dimension 30, the unit ball holds almost nothing. The formula is on screen, and this curve is plotted from it exactly. It gets worse. In high dimension, almost all of a ball's volume crowds against its skin. The middle is practically empty. Flat pictures quietly lie about all of this. Intuition trained on oranges fails. So mathematicians stopped trying to see packings and started trying to certify them. To find algebra that speaks about every possible arrangement at once, sight unseen. That is the move that changes everything. And it is where our story's tool enters. Here's the certificate game invented by Cohn and Elkies, building on Gorbachev. You choose one function, e tayetv. Its graph is this amber landscape over distance. Below the horizon sits its mirror partner, f hat, the Fourier transform of f. Do not fear the name. For this film, it is simply a second curve, computed from the first, that measures the wave content of f. Your function must pass 3 gates. Gate 1. Beyond distance 1, f must stay at or below 0. Gate 2. The mirror curve must never dip below 0, anywhere. Gate 3. At the center, the mirror value must be positive. pass all three gates, and a miracle follows. The number f at 0 divided by f hat at 0 caps the density of every packing in that dimension, every packing that exists, and every packing that could ever exist. Watch the exact game in dimension 1. Take the tent function, 1 minus the distance, then 0. Its mirror partner is this curve, called sinc squared, and it is never negative. All three gates pass. Both center values equal 1, and the certificate reports a ceiling of exactly 100%. Precisely right, because on the line, segments really can fill everything. The game is honest, and in dimension 1, it is even sharp. But why should three sign rules command every packing in existence? Because one quantity can be counted in two worlds. Put packed centers on the line, spaced one apart, and total the value of f over every pair of centers. Call the total s. Count in the physical world first. Each center paired with itself contributes f at 0. Every other pair sits at distance 1 or more, and gate 1 forces every one of those terms to be 0 or negative. So s is at most the number of centers times f at 0. Now count the same s below the horizon. A classical identity, Poisson summation, re-expresses the total as a sum of mirror values over evenly spaced frequencies. Gate 2 makes every one of those terms 0 or positive. Keeping only the central one gives s is at least the number of centers squared times f hat at 0 divided by the length of one cell. The same number squeezed from both sides. Divide, and the ceiling appears. Density is at most the ball volume factor times f at 0 over f hat at 0. Watch the numbers on our chain. Above the horizon, the total is exactly 1. Below the horizon, exactly 1. The vise closes perfectly. No packing anywhere can slip through it. How good is this game? In 2016, Maryna Viazovska found a magic function for dimension 8 whose ceiling touches an actual packing called E8. What you see now is real data, all 240 nearest neighbors of one sphere in E8 projected onto a plane. 8 rings of 30 points. The golden ratio hides in their radii. The ceiling and the packing meet. Dimension 8 is solved. Exactly. Within a week, the same method cracked dimension 24. The Leech lattice, where every sphere touches 196,560 others. This work earned the Fields Medal in 2022. So the certificate game is not merely good. In dimensions 1, 8, and 24. It is perfect. Those are the only high dimensions humanity has ever finished. A dream took shape. Maybe magic functions exist in every dimension. Maybe this one game settles sphere packing forever. Whether that dream can survive is exactly what the new theorem decides. Ask the question properly. As dimension grows, densities shrink exponentially, so what matters is the rate. The number alpha in density at most 2 to the minus alpha d. Higher alpha means a stronger ceiling. The 1978 record of Kabatianskii and Levenshtein, alpha equals 0.599. The certificate game always performs at least that well. But what is the game's own limit? The best rate any certificate can ever certify. For decades, nobody knew. Then a strange clue arrived from physics. Researchers studying the modular bootstrap, a toolkit from conformal field theory and quantum gravity, ran into the very same mathematics. Extrapolating their numerics, they predicted the game's true rate, the square root of e over 2 pi, a precise constant surfacing in gravity research with no proof attached. That prediction, made in 2020 by Afkami-Jeddi, Cohn, Hartman, Delat, and Tajdini, is the number the new theorem was built to reach. Here's the theorem, proved in 2026. As the dimension goes to infinity, the certificate game's value, taken to the power 1 over d, converges to exactly the square root of e over 2 pi, about 0.658. This says two things at once, and they must be kept separate. Phase 1, a new record. The game does beat 1978. The exponent moves from 0.599 to 0.6044. The first improvement of the general sphere packing ceiling in 48 years. The needle moves. Phase 2, a wall. No function passing the three gates, none that exists, and none that could ever be written down, certifies a rate beyond 0.6044. The tool that solved dimensions 8 and 24 now has an exactly known strength. The rest of this film earns both faces. First the wall, why nothing can beat it. Then the touch. A certificate that reaches it. Obstruction, then construction. That pair is what exactly means. Take any function that passes the 3 gates, we will squeeze it into a corner. Step 1, balance. Rescale distance so that the curve's center value equals its mirror partner's center value. Like leveling the 2 pans of a scale. Balancing changes nothing about the certificate's quality. It only chooses honest units. Step 2, subtract. Define G as the mirror partner minus the curve. This G is special in 3 ways, and you can watch each one. Its own mirror is itself with a minus sign, an anti-self mirror function. Its center value is 0 because the pans were level. And beyond the balanced radius, G is never negative, because out there the curve is at most 0, while its mirror is at least 0. Now the trap. The total signed area of G is exactly 0, so its negative part and its positive part carry equal mass, half and half. But G can only be negative inside the balanced radius. Half of everything G is locked inside that inner ball, and what you see is not a sketch, it is the exact function, sint squared minus tent, from our dimension 1 certificate. Every property holds on screen. One question remains. How small can that prison be? The first attack is the natural one, and it fails in an instructive way. If half the mass hides in a small ball, compare total size against peak size. The Cauchy-Schwarz inequality turns mass in a small region into a comparison of norms. Single numbers, each summarizing the whole function. Push that root as hard as possible. Sharpened inequalities, Gaussian eigenfunctions, the best constants known. The ceiling it certifies stalls at the square root of e over 8. 0.583, short of 1978, let alone the target, and there is a reason it must fail. And explicit anti-self mirror functions exist with enormous norm ratios whose negative mass sits far from the center. A norm is a scale reading. It tells you how much, never where. Watch the pool pour into the measuring cylinder. The reading is identical no matter where the mass came from. But the location was the entire question. The proof needed an instrument that sees position and mirror symmetry at the same time. That instrument is a change of viewpoint. Plot G against the logarithm of distance and package it as a function on a strip in the complex plane. Each horizontal line of the strip reads the function at 1 exponent height. This is the Mellin transform. What matters is what it does to the mirror rule. Inside this strip, taking the Fourier transform becomes a reflection. Top edge exchanged with bottom edge times an explicit factor built from the gamma function. Our G is its own mirror up to a minus sign, so the strip's 2 boundaries are chained together. The top edge is tame, bounded by 1. The bottom edge is ruled by the gamma factor, and the balancing 0 at the center exactly cancels its one dangerous pole. Now a classical principle. A function's size inside a strip is at most a weighted average of its size on the 2 edges. The weights are called harmonic measure, and in the limit they follow this curve, plotted from its formula. Feed in both edges. Take the average. Out comes a decay rate. The logarithm of pi squared times c squared, where c sets the prison radius in units of root, d. Watch the sign. The rate is negative, meaning exponential exclusion, exactly when c is smaller than 1 over pi. Below that radius, the strip starves the interior. The trapped half mass would have to be exponentially small. It cannot fit. As the dimension climbs, watch the pool try. The prison can never be smaller than 1 over pi times root d. The wall stands. An obstruction is only half of exactly. Does anything touch the wall? Start from the calmest function in analysis, the Gaussian bell. It is its own mirror image, and it passes the strip untouched. But the sign radius it can produce sits at 1 over root 2 pi. 0.399 in wall units. Too far out. The proof reshapes it inside the strip, multiplying by a chosen profile of dilations. Squeezing mass among radii, like retuning a bell by shaving rings of metal. Every unit of reshaping costs damping. The gamma factor's decay is a budget. Saturate the budget, and the ideal shaving profile is this exact trench. Minus e to the minus 2a over 2 a squared cosh a. Its total effect on the sign radius is an integral with a closed answer, minus 1/2 the log of pi over 2. An identity that comes down to Wallace's product, the 17th century formula for pi. Apply the shift. 1 over root 2 pi times root of 2 over pi is exactly 1 over pi. The bell's last sign change lands on the wall. The slide you are watching is the asymptotic picture. The endpoints are exact. One problem remains. The ideal trench overspends its budget far away, so the proof trims it and adds a tiny positive shell on a distant interval. An interval so that no frequency can resonate. Decay returns everywhere, and the target does not move. 3 sign-selecting polynomials then split the reshaped bell into a matched pair and a partner. A certificate whose gates all pass, whose radius touches the wall. Two constants now mesh like gears. The wall says, the certificate's quality per dimension is 1 over pi times root d, no better. And by the construction, no worse. The geometry of high dimension says the unit ball's volume, taken to the power 1 over d, behaves like root of 2 at pi e over root d. Multiply, halve for the radius, and root d cancels. Root of 2 pi e over 2 pi, which is exactly the square root of e over 2 pi. The strange constant is no longer strange. Pi comes from the wall, e comes from the volume of spheres. As an exponent, 0.604400544, and the digits continue. The accompanying lean formalization states precisely this limit, machine-checked down to an explicit decimal interval, and we verify that the formal statement matches the manuscript theorem. That is what formalization certifies here. No more and no less. The same construction also settles a second long-standing question, called sign uncertainty, with the same answer. 1 over pi, one mechanism, two frontiers. Now the honest map. What this theorem does not say. It does not reveal the densest packing. The best packings anyone can actually build sit near 2 to the minus d. A 2025 breakthrough by Klartag improved the polynomial factor, not the rate. The new ceiling stands at 2 to the minus 0.6044d. Between them lies an exponential no man's land, growing like 1.32 to the power d, and the truth is somewhere inside it. Nobody knows which side it favors. This theorem does not construct better codes, it does not weaken any encryption, it is a limit on proofs, not an algorithm. And it does not make the certificate useless. The game still holds the very record it just set. What it does say is sharper than all of that. To ever push the ceiling further, mathematics must leave this game behind. Richer certificates, new ideas, the frontier is now exactly surveyed. Either far denser packings exist than anything ever constructed, or the ceiling must come down by tools not yet invented. Return to the beginning, a wall of spheres, a number frozen in 1978. You now know what moved it. A signal is a point. 1,000 dimensions is a list. Packing is communication. One function with 3 sign rules judges every packing at once. Balancing any such function traps half of a difference inside a radius. A strip of exponents proves the trap can never shrink below 1 over pi times root d. A reshaped bell touches that wall, and the square root of e over 2 pi falls out of pi and out like a closing gear. The first movement in 48 years, and the exact measure of the tool that made it. The wall at 1 over pi is both a triumph and a boundary. This is precisely how far the magic functions go. Beyond it, the spheres keep their secret. Somewhere between two ceilings, the true tightest packing of high-dimensional space is still waiting to be found.